So, today I will tell you about something that's pretty cool, PV diagrams, or pressure volume diagrams. It's basically a way to represent thermodynamic processes in terms of the pressure and volume. And I'll mostly be discussing on how the area under the curve is equal to the work. So yeah, just a quick introduction. Let's get into it. So PV diagrams, it's literally just a graph of the pressure as a function of volume. That's basically it, right? So as you can graph any type of thermodynamic process using this if you know the pressure and volume. But the main reason why we use these is because the area under the curve of whatever graph this is is the area, right? This area is actually equal to the work done. And we're probably like, whoa, how'd you get that? Let me show you, right? So basically, a good way to think about this is through an isobaric process, right? And for anyone who doesn't know, that's basically a thermodynamic process where the pressure of the system remains constant throughout the whole process, right? So let's say isobaric, and then oh my god, we'll draw the graph of that, right? Pressure, volume. Well, pressure is going to be constant. We know that because pressure is going to be constant in this process, and the volume can change, right? So let's think of what work is defined as classically. Well, work is force times distance. We all know that. And using what we know about pressure and force, we know pressure is a force divided by area. Ignore the really bad F and A. Yeah, so then we have work. Rearranging that, we get work is equal to the pressure times the area times the distance, right? All pretty good. Well, let's think about what this really means, right? Specifically this term right here, this area times distance term. Well, if we rewrite this in a way where we have area times d of x, right? We then basically, this is the volume. This is the increase in volume. This is basically just the volume, right? And a way to visualize this is, so imagine we have a piston like this, right? And well, it's not supposed to be this big. Let's just say we have a piston like this, and we end up having a cylinder with a bunch of gas inside, and the piston moves up and down, right? So the pressure of this piston is going to remain constant, right? But the volume will increase. So if we imagine the area multiplied by a change in the distance, we're basically saying the area of this piston, right? So the face of this piston right here, multiplied by the distance that the piston moves, right? So this will be d of x, right? That was by accident. This will be d of x. So right now we literally have area and then d of x, right? Because that's what we're multiplying. And that essentially, if we imagine this, right, as the area, and this little thing is d of x, right? We essentially just got a volume, right? We just have the volume, right? Or d of v, right? So we have a volume right here, because area times, this is essentially base times height, right? Which gives us a volume. So if we do all this again, I'll actually keep that. So if we can rewrite this as work is equal to the pressure times d of v, where v is volume. And so if we want to find out what work actually is, right, we would do the work is equal to the integral where upper limits of a volume final. Let's just define this as VF. Let's define this as VI. Volume final, this is volume initial. And then the P pressure times the D of V, right? So this is the general form for, that's basically the general form of what happened? Someone gotta tell me what happened. Okay, that's the general form for work in these types of graphs, right? And we can see how we got that. But for isobaric though, we know that the pressure is constant, right? So we can take that out of the integral. So this is like, all of this is just for normal. Why did that happen? All this is just for normal work, right? But for isobaric specifically, if we want to just add on to this, right, we can take pressure out of the integral because it'll be constant. So you have pressure integral of VF I rate of volume, and we know that that is literally just pressure, then volume final minus volume initial, and volume final, volume initial, that's literally just pressure, change in volume. So the work for an isobaric process will be the pressure times the change in volume, but the more general form for work will be the integral with upper limits volume, the final volume, and lower limit volume initial, and the pressure, and then the D of V. So yeah, I hope that made some sense, right? I don't know why that keeps happening. I really don't know why that keeps happening. Yeah, okay, never mind. But yeah, I hope that made some sense. This is basically PV diagrams in a nutshell, and specifically how work is the area under the curve. Thanks for watching. I'll talk to you next time.